You may have even bigger circuit also. But that
Yes,
discussion
yes.
was basically about gate, and that
Gates.
too two input not gate, NAND gate. Somewhere it may come that all the analysis are done with two input NAND gate as a standard. Okay, but it doesn't mean that always in the chip there will be only two input NAND gate. Maybe three input or four input also. Normally it doesn't exceed this number, because again the pull down network will be connected in series, and then TPHL will be very larger, longer. Understood?
Yes, yes.
Okay. Now we are here. This is also discussed. So I am going further. Direct path current is discussed. You have understood. So I'll go further. The equation also regarding this I have discussed, and is here. I average E short circuit is I average into VD, and if you integrate, then you get this expression. This expression I just wrote earlier, but now this expression I wrote. This expression, but its derivation is there. If you want, I can go back and this from here onwards, if you want to, because this is not discussed. Only I have said that there will be direct path current, because both the MOSFETs and MOSFET and PMOSFET will be on for a brief period of time, and hence VD will be connected to ground for that time, and hence a current spike will be there. That current is short circuit current, IC, or direct path current. Okay. So if you want to know further regarding this, then we can go slow and discuss. This analysis leads to the conclusion that the short circuit dissipation is minimized by making the output rise and fall time larger than the input rise and fall time. This is to be understood. This did I discuss earlier? No, I don't think. It's not discussed. So again, I have come here. Let us. This is dependent on rise time and fall time. The direct path current, and hence the power, direct path power, is dependent on the rise time of the input and fall time of the output. Okay. So how it is, you can understand from these diagrams. The short circuit, also called direct path current, is significant if the output load capacitance is small, and or if the input signal rise and fall times are large. Okay, input signal here. How it is possible to understand? Tell.
So if the rise time is longer, then for longer period, the VDD and ground would be on a direct path.
Direct path will be for a longer time. That is there. Very good. Case 1. Let us study case by case. 0 to 1 transition at the input. This is the left hand side. You have the 0 to 1 transition of the input, and the CL is very large. This value of CL is large, so that output TF, fall time, is quite longer than the input TR, rise time. This is TR. And Vout does not drop quickly. During low to high transition, output will be falling. No? Yes or no? It is happening here.
Yes, sir.
As the VSD of the PMOS device is approximately 0, during that period, the device shuts off without you are delivering any current. The short circuit current is close to zero in this case. Now case 2, 0 to 1 transition at the input and the CL is very small. In that case, what will happen? And the output TF is subsequently smaller, substantially smaller than the input TR. Obviously, if capacitance is small, value of capacity CL is small, then that can be charged as well as discharged very quickly. So here it is going to discharge very quickly. So TF will be very small compared to TR. The VSD of the PMOS device equals VDD. For most of the VSD of the PMOS device, VD for most of the time, guaranteeing the maximal short circuit current equal to the saturation current of the P MOSFET. This clearly represents the worst case condition. Understood? ISC is Imax. Dissipation due to direct path currents. The conclusions of the above analysis are confirmed in this figure, which plots short circuit current through the NMOS transistor during a low to high transition as a function of CL. CL's different value of CL is taken. CL 20 femtofarad, 100 femtofarad, and 500 femtofarad. This y-axis is your I short circuit. Okay. This all we have discussed, so you can understand that short circuit current will be there will be a higher
Spike.
Higher spike will be there for short value of low value of CL. This analysis leads to the conclusion that the short circuit dissipation is minimized by making the output rise fall time larger than the input rise fall time. That is one conclusion. On the other hand, making the output rise fall time too large slows down the circuit. That is also a problem and can cause short circuit currents in the fan out gates. Okay, fan out gates also there. It is going to drive another gate also. Okay, if it is making very slow change at the output, then it will be a problem in the gate which is being driven by this gate. Okay, so this presents a perfect example how local optimization and forgetting the global picture can lead to an inferior solution. Means you cannot think of only of your gate, that yes, my gate is or my circuit is consuming less power, less dynamic power. You are optimizing, but you have to consider the other gates which is going to be driven by this gate also. Globally, you have to think. The short circuit power dissipation is given by P short circuit equals to I average into VDD. For the input waveform shown in this figure, so T1, T2, T3 is here, which depicts the short circuit in an unloaded inverter. The unloaded and loaded, you understand. This fan out is less, or fan out less gate it is. It is not connected to drive any other gate. That is what it means. What you have only CL equals to what? Tell. Drain diffusion capacitance only you have. Yes or no?
Yes, sir.
Yes, sir.
You don't have air capacitance or you don't have the COX of fan out gates. In that case, I average can be written like this. 2, because you have a rise and fall, it is symmetrical, it is considered around T2. T1 to T2 time distance and T2 to T3 time distance is considered same. So term 2 is coming for that, and you are integrating I square. Sorry, I dt this from T1 to T2 plus 1 upon T I T22 dt. So from this integration, if you do integration properly with uh, this assumption, assuming Btn equals to minus Btp and beta n equals to beta p equals to beta, and the behavior is symmetrical around T2. This is the T2. When rise time and fall time is happening, I mean, here it is rising, the spike, current spike, while spiking up is same as when spiking down. Okay, if it is symmetrical, it is not rise time and fall time, it is rather when spiking up and spiking down is same, then integrating at the end you will get this expression what I have shown earlier. So will you look at this and find out any typographical error?
Yes, sir.
Look at, and then we'll go to the next slide. We are getting average, I average here. Okay. Then you have to multiply with PDD to get the direct path current. Is it done? Some more assumption may be required here. See, with B in equals to this and T1 equals to this. Thus, for an inverter without load, assuming that TR equals to TF. This TR, when it is both same, we are writing TR equals to TF, TF. In this expression, we have written a TR TF, either TR or TF. If you consider both same, rise time and fall time, means this one. If this TR is equals to TF of the input waveform, then we write instead of TR or TF, TF, and we get this is a TSC equals to beta by 12 into VD minus 2 VT whole cube TR or TF divided by TP. This TP is period. Period of the waveform. Period means here TP is not propagation delay. This is from here to here. Another transition, transition in the input is starting up to that point. This includes TR plus TF plus period. This is, sorry, pulse width. This is pulse width. And total is pulse period. From here to here is period. Okay. Is it understood? Himanshu Shugra?
Yes, sir. Yes, sir.
We get this expression this way. So the power dissipation due to the short circuit currents is minimized by matching the rise and fall time of the input and output signals at the overall circuit level. This means that rise oblique fall times of all the signals should be kept constant. And for that, how the say inverter has to be designed? Tell me. We have already discussed. Can you recall how we are going to ensure that? You have to size the transition in such a way that in this technology, how much sizing should be there? In 0.25 micrometer CMOS process, an inverter to be sized how? Let me see whether you are recalling or not.
So
Sir,
TR
V
point
threshold should be VDD by 2.
PM equals to VD by 2. Very nice. 2. Sizing wise, this is the VM you are going to do. Sizing wise, how in this technology generation we done?
WL equals to 3.4.
Yes, very good. So this is what we have to do so that direct path power or short circuit power is minimized. Sorry. Making the input and output rise times of the gate identical is not the optimum solution for that particular gate on its own, but keeps the overall short circuit current within bounds. This plots shows the short circuit energy distribution of inverter normalized with respect to the zero input TR dissipation as a function of the ratio R between input and output. TR for the input and TF for the output. So normalized power for VD 1.5 volt, 2.5 volt and 3.5 volt. Here short circuit power dissipation plot. When the CL is too small for a given inverter size R greater than 2, 3 for VDD equals to 5 volt, the power dissipation is dominated by the short circuit PSC. When input TR equals to output TA, most power dissipation occur due to charging and discharging of CL, and only a minor fraction, less than 10%, occurs due to ISC. So this all is giving some idea. Yes. When CL is too small for a given inverter size, the power distribution is dominated by the short circuit power. When input rise time equals to output fall time, most power dissipation occurs due to charging discharging with dynamic power, and only minor is short circuit power. Okay. Yes or no? Understood or not?
Yes, sir.
All these things has
Yes,
to
sir.
be kept in mind while doing the circuit design. So static
Sir,
or
excuse me.
steady state. Yeah.
Sir, can you continue in next class, sir? We have a class now.
Okay. Next class on when? Tomorrow. What is the date tomorrow?
Sir, 14.
14th. September. Okay.